We have an object. Up to now, we have mostly been talking about, pushing and pulling forces. We're now going to hang something on two cables. Let me, I'm trying not to completely do number 4 for you, but we're going to get pretty close. So I've got something hung on two cables, and so the force of tension in each of these cables, well, okay, let's back this up a second. He's back. So if we have something hung on one cable, can you find the force of tension in that one cable?
Yes.
Okay. How would you do that? Mass gravity, force of gravity. Yeah, you would look at this situation and you would say to yourself, this force of tension is on the y-axis. There are no forces shown on the x-axis. Therefore, the sum of forces on the y, if this is not moving, is equal to 0, and that's equal to all the forces up minus all the forces down. All the forces up are the force of tension, and the only force down is the force of gravity. So I can figure out the force of tension. Good job, self. That's easy. What if we now have something hung by two cables, which is where we find ourselves on number 4? Well, it may not surprise you that this is still going to come down to a sum of forces. But if we break apart this force of tension, for each one of these, and I'm going to label these force of tension 1, force of tension 2. For each one of these, we in fact have a force of tension 1 on the x and a force of tension 1 on the y. Agreed?
Yes.
Okay. So, what we can say, well, first of all, so if you've been told that this object is not moving, it's just suspended. We know that on each axis, the sum of forces has to equal what?
0.
If it ain't moving, the sum of forces on that axis is 0. So I'm going to start with the x-axis, sort of as almost like doing a proof. This is going to become important when we do number 5, because the x-axis will hold a solution for us. So we know it's not moving laterally. So the sum of forces on the x-axis is 0. And this is all the forces right minus all the forces left. All right. Well, what are the forces right and left? Well, force of tension 2 on the x minus force of tension 1 on the x. We know that they're equal and opposite. That's nothing earth-shattering. What is the force of tension on the x? Oh, okay. Here's where I've laid a nice little trap for you. Sorry about that. Let's say that we're given the angle with the wall. This is where you got to pay such careful attention to how the angle is identified. Because angle with the wall versus angle with the ceiling is going to give you the angle or the complement to the angle. And I don't remember which way it's written in 4.
The angle to the vertical.
To the vertical, so angle to the wall. Okay.
I thought
So
on the object down here.
no, it's going to be the object or the angle between the cable and the sort of suspending structure. All right. So we've got that angle with the wall, which means this, so let me pick another color here. What do I have? I'll do bright yellow. This would be the complement of that angle. So you do have to be a little bit careful. So we can either take, and I'm going to sort of fill in with, well, no, I'm not. Remember that we can, in fact, move this vector to here. And of course, this interior angle is going to be the same as the one we were given. This takes a little bit of trig maneuvering to make sure you don't screw up your angles.
Oh, I did the
Okay, good. So yeah, it's if the angle's given with the wall, that's going to be the same as the angle between the cable and like a center line straight up. Does this make sense to everybody? This is almost like analytical geometry. You're just moving around a bunch of angles. So, what is then Ft1x? Well, it's equal to the force of tension 1 times sine theta. It's also, and this is going to become important, the alternative would be Ft1 times 90 minus theta cosine of 90 minus theta. So in other words, cosine of the complement. Does that make sense? Okay, but again, this didn't really get us anything groundbreaking because we're not going to get to force of tension from the x-axis because there's nothing to compare it to. You know, we just proved that the force of tensions are equal and opposite. Woohoo! Who cares? We still don't know the magnitude of the force of tension. So because on the, and I'll use a nice blue here, because on the y-axis we have F of gravity, which equals, of course, mg, as long as we're given mass, we have a number to attach on the y-axis. And that's what's going to allow us to find force of tension. So, sum of forces on the y, if we are told that this thing is just hanging suspended, it is also 0. Thanks. Okay. Do I want actual mass? Yeah, I'm going to say it's 10 kilo. No, I don't want the actual mass from the problem. That would get too close to actually doing the work for you. This is just a generic example that closely mirrors the problem. So, what is the force of tension on the y? Whoops. Force of tension times, well, here's our y, and we said theta is right there. Force of tension cosine theta. So 2 times force of tension cosine theta minus an Fg equals mg. Okay. So, how does we solve for force of tension? Well, I'm glad you asked. I think most of you can probably see it already. So we're going to knock that off. So now we've got, we know that the sum of forces on the y is 0 because it's not rising or falling. So 0 equals 2 ft cosine theta minus mg. So mass gravity equals 2 ft cosine theta. You've now got the ruby slippers, Dorothy. And so mass gravity divided by 2 cosine theta will give you your force of tension in each cable.
In each one or
in each one.
Should
They're identical.
Right, but didn't we change it to the sum of force of y equals 2 times the...
Yes, and there's our 2.
Right, so doesn't
So mass gravity divided by 2 cosine theta.
That's divided by...
Yes, it's oh, did I say multiplied by?
I don't know, I just...
Okay. No, it's divided by. What?
Because
Okay.
there's 2 strings, so...
There are 2 strings, and this is where we're going to get out the tension board. So mass gravity divided by 2 cosine theta gives us the force of tension in each cable. Because each cable is carrying half, essentially each cable is carrying half the weight for the whole system.
So if it were just one cable?
Yes. But you wouldn't have a cosine theta because if it's just one cable, it's going to hang straight down. No, there's no depends. It's going to hang straight down. If you got, huh? Mhm.
Okay. 'Cause I mean, I just did it like just a general trig function. Like I found that it was like a right triangle. And I knew
No,
what
you need
side
to, so that's a
was.
great question. You need to become accustomed to showing the sum of forces on each axis. You know, you don't have to do a whole lot with the x-axis because there's no action there. It's boring. But doing just, doing just that on the x-axis to set aside, because here's the facts. Right now, you can get away with what you're doing. You won't be able to after the next section. So you have to get in the habit of doing that, sort of proving what each force is, proving where it is. So, questions on this? So go ahead and you should be able to do number 4, and then, so nobody took my advice and got number 5 to the point where you could solve it if only you had the angles.
Well, here's the thing. I looked at it, I drew the picture.
Okay, hold on. Yeah, the right angle's at the center.
Yeah, that's fine.
So, but I'm pretty sure, hold on, relax. Tension in one cable is twice the other. What are the magnitude of the, oh, okay, that's right. Because you can find, so you can find either, okay, so we don't know where the angle is and we don't care. We're gonna end up finding the angles. We can find the angle with the wall or the ceiling. But if we use that angle, then FT1 sine theta 1 plus FT2 sine theta 2, because see, theta 1 and theta 2 are not the same. Minus mass gravity equals 0. So let's shrink this. Okay. So, well, you can designate your FT1 or 2 as you see fit. So if that equals, if FT1 equals 2 FT2, then we can say 2 FT2 sine theta 1 plus FT2 sine theta 2 minus mg. So it is not, in fact, 3 FT2 or 3 FT1, depending on how you name them.
Wait, well, if theta's
Different.
not if you use the 45-degree angle in the middle. No, to kind of.
But it's not a 40, it's, don't do that. Don't even dare.
It's a 90-degree angle.
Yeah, but if you split that 90, you're not splitting it in 45 and 45 because the angles on the other side are not the same.
Yeah, but, well, actually, the other side of the angles won't matter because you've got the if you've got the 45. We can do
There's no 45 here, buddy. Here, let's prove it. Can you factor an FT2 out of that? Yes.
Yes.
You need to employ liberal use of parentheses,
Well, yeah.
and then you can factor an FT2 out.
Oh yeah.
Not in this current state.
No, but it only takes another step of initiative on your part.
True.
Okay, so take that step of initiative. At the end of this chapter, you should be so fluent with this. I want you to be able to toss these pieces on the page and pick your way through the puzzle. And especially at the end of this chapter, we start doing a lot of work where it's like, okay, what are all the things I know? Who here has solved one of those stupid logic puzzles that they give smart kids in middle school? You know, Susie lives in a house that's the same color as her favorite vegetable. Bobby likes eggplant. Joanne lives in the house next to the person who likes tomatoes. Do you remember these?
Yeah.
Yes. Oh my God. That's what these are like. You know, no. You have a bunch of pieces of information and you've got gaps in that information and you're figuring out how you can use pieces of that information to get the next thing you need to know. So at this point, we can get an expression for FT2. We've taken all the information we had, and all we knew was that it wasn't moving vertically, and we knew that the force of tension in one cable was twice that of the other. And that gets us an expression, so we would do mg minus, or mg, I'm sorry, divided by this equals force of tension 2. So now if only we had, if only we had those angles, life would be grand. So what I'm going to tell you is that the secret to the angles lies on the x-axis, and this I will actually walk through with you. I have not done this in a year. I am going to be bumpy as all get out on this. I don't remember how to do it. I'm going to blind stumble my way through it. You get to stumble with me, okay? Oh, you know what? Get used to it, buddy. Seriously, it's good for you. It's good for your brain because your brain is fighting to make meaning out of things that are confusing, and that's how you build brain connections. Okay, so what do we know about the x-axis? Oh, you're still here?
Wait, how were we able to take out the FT? Oh, because we substituted for the FT1. That's okay. That's right.
Yeah, and you know what? I should have highlighted that little
I was like,
move.
FT1, the other one's FT2.
So we took this knowledge and used it to make a substitution there.
Yeah.
Okay. So here, what do we know on the x-axis? It's not moving laterally. There is no movement on the x-axis, so it's 0. We also know that it is equal to all the forces right minus all the forces left. And we know, furthermore, that, FT1, so we know that 0 equals, well, the force right is FT1 on the x. The force left is FT2 on the x. Using this angle, that would be cosine. So 0 equals FT1 cosine theta minus cosine theta 1, FT2 cosine theta 2. Okay. Well, can you get those across the sign from one another? Of course you can. Don't be ridiculous. FT1 cosine theta 1 is equal to FT2 cosine theta 2. I'm going to come back here and I'm going to borrow this piece because that's going to be kind of critical. Copy, paste, just as a reminder. So that means we can substitute something for this, so we can eliminate a variable. Okay, so that gives us 2 FT2 cosine theta 1 equals FT2 cosine theta 2. Oh, I think I remember how this goes. Now, can we eliminate our force of tension here? Heck yeah. Gone. Factor out, divide both sides by FT2. What do we have now? We have the deep conviction and calming reassurance that 2 times the cosine of theta 1 is equal to cosine of theta 2.
It's a 30 to 60.
No, it's not.
What would it be?
I'm not going to tell you that. I'll finish the proof on this and I'll post it.
So I was thinking, I thought it was a 30.
It's not a 30-60, but that's where all the smart kids go. Oh, I see it. It's a 30 and a 60. It's not. It's real close to a 30 and a 60, but it's not.
Like, there's probably some weird
It's a weird angle. Of course it's a weird angle. Are you kidding? We're hanging mastiffs from the ceiling. Why would it not be weird?
Yeah,
Okay, so it's not like a
90 degree angle is a 3, 4, 5.
Yeah, it's not that easy.
Yeah, so there's
It's
no way-
not that easy.
That's what I'm saying. That's what
Yeah,
I'm
you can't logic your way backwards into it like that. You actually have to do the sort of analytical geometry proof. I'll finish. I know it's mean. It's physics. Get used to it.